Hi, my name is Lily Adlesick, and this is my lab for Physics 2211 Lab 5, Choose Your Own Adventure. The purpose of this lab is to investigate and compare the motion of an object sliding down ramps of various degree angles from the ground. The fundamental physical principle we will be studying in this lab is Newton's second law, or the momentum principle, which states that the acceleration of an object is dependent upon the net force acting upon the object and the object's mass. Our results preview is that as the angle of the ramp increases, acceleration increases. However, we do not include friction in our computational model, thus the acceleration of the marker falling down the frictionless ramp is equal to 0. In reality, forced friction acts parallel to the ramp surface and opposite the motion of the marker. On the left here, we see the applicable models to our lab, the 3 ramp angle degrees we will be testing, and how we can break up a vector, namely that of forced gravity, into its x and y components respectively. Fg in the y direction equals mg cos theta, and mg in the x direction equals mg sine theta. And on the right, we see the important equations that we will be implementing into our code. dp dt equals F net, final position equals initial position plus average velocity times the change in time, or delta t, and final velocity equals initial velocity plus net force divided by mass times the change in time. Now for the experiment. The system is the object sliding down the ramp, which in this case is a marker. The surroundings is everything else. Our procedure is to edit the computational model from Lab 1 to account for the net force acting on a marker as it slides down a ramp. In Lab 1, when we were rolling the marker along a meter stick with a constant velocity, the net force was 0 newtons. And then we repeat this step for 3 different angle degrees, 30, 45, and 60. And I've included their equivalent measurements in terms of radians. Then we compare our results and analyze how the angle of the ramp affects the motion of the marker. Our key assumption in this lab is that there is no force friction acting on the object. The ramp is smooth enough to neglect force friction. Here are the initial conditions and system properties for our GlowScript code. The marker mass is 1 kilogram, the original position is 0 meters, and the original velocity is 0.256, and time is set at 0. Here you can see the equations from earlier implemented into our code, where above we calculate the net force, and secondly we apply the momentum principle, which is our fundamental physical principle. Here's a better look of how we added the equations into our code based off of the given equation and our variables in GlowScript. Here's how we edit the net force equation for the 3 different degree angles to simulate the different degree angles between the ramp and the ground. Notice how we break up net force into its x, y, and z components separately, based off of the model we viewed earlier. Therefore, the resultant net force calculated here in our GlowScript code will be a vector. Here are resulting computational models for a degree angle between the ramp and the ground of 30 degrees, 45 degrees, and 60 degrees respectively. As you can see, all these graphs are the same. The axes on these graphs represent position versus time, meaning that the motion of the marker sliding down the ramp is the same regardless of the angle between the ramp and the ground. Here is the shared velocity versus time graph between the 3 angles of the ramp, and as you can see, as the marker moves down the ramp, velocity is not constant, and this negative velocity slope means that the object is slowing down over time. Finally, for our analysis, our conclusion from this lab is that the motion of the marker or any object sliding down a ramp is the same for all angles of the ramp between the ground, given all other variables are held constant. One possible source of error in our data is not including force friction acting upon the marker sliding down the ramp. A couple what-if scenarios for deeper understanding. What if the ramp made a 90-degree angle with the ground? Then the marker would act as a free-falling object, as we saw in our Physics Lab 2, and the acceleration would be at its maximum. What if the ramp was longer? Then the time it takes the marker to reach the bottom of the ramp would be longer. That's the end. Thank you for watching.